Students, in the previous segment, we assumed that in the expansion of a plus b whole to the power n, this binomial expression, if the representative terms are like these blank boxes, from the fact 0, we got that all of these terms will have a form ki a to the power x b to the power y, right? Each of them will be expressed in this form. For convenience, we will replace y by r. As I said here, I don't like y, so hope you understand. We'll replace y by r. This is not that significant, but for convenience, ki equals to a to the power ki into a to the power x b to the power r in place of y. Okay, so this is the representative term. People who haven't understood fact 2, it was simple. Before going to fact 2's review, we can say that this a and b, this can be any real numbers, okay, positive or negative. Okay, so you can express x minus y whole to the power n as this form as well, like you'll write x plus minus y whole to the power n. So here b is negative, right? So a and b can be any real number, positive or negative. So in fact 2, we learned that if the exponent or degree of this binomial expression is 2, then all of the terms of the expansion of a plus b whole to the power 2 will have a degree 2. Here 1 plus 1, 2. Okay, similarly, we got that at last in the expansion of a plus b whole to the power n, all of the terms degree will be equals to n, right? This is what we got in fact 2, and how we explained there. So if each of the terms has this kind of form, then the degree will be x plus r, right? That will be equals to n. Remember, we wrote there x plus y equals to n. So from this, replacing y by r, we got x plus r equals to n. And here, can we replace x equals to, can you say x equals to n minus r? Yes. Okay, so now all of the representative terms will look like ki a to the power n minus r b to the power r. Why? We replaced this x with n minus r. So this will be the form of each terms in the expansion of a plus b whole to the power n. Okay, now we are moving towards fact 3. In that case, we can say that a plus b whole square, in this case we elaborated it like this. Okay, why have I written this again? See here, how many times ab appeared? Twice, right? And we got a square plus 2ab plus b square. ab appeared twice, so this is the coefficient of ab, shohog, ab is shohog. So this is the coefficient of ab. How many times b square appeared? Once. So the coefficient of b square equals to 1. Similarly, a square appeared once, the coefficient of a square equals to 1. And we got in a plus b whole cube that a plus b into a plus b into a plus b. See here that how many ways can we get a cube? If we take a from first element, a from second element, and a from third element, we get a into a, that is a cube. Can we get a cube from any other combination from these three? No. So there is only one combination, so only once a cube will appear in the expansion of a plus b whole cube, so the coefficient is 1. Similarly, we can get here a b, a into b. We can get a into b into a into b into a. Again, we can get b into a into a. So how many times did we get a square b? Thrice. So since a square b appeared thrice, so the coefficient is 3. Similarly, from symmetry, we can say that AB square will appear thrice. So that's why the coefficient equals to 3. And at last, similar to A cube, we'll get B cube only one way. So B cube will appear only once. So that is why B cube has a coefficient 1. So what do we get from this? We get that the coefficient of each term refers to the number, how many ways that term appeared, right? AB square appeared thrice, so the coefficient is 3. A square B appeared thrice, so the coefficient is 3. AB appeared twice, so the coefficient is 2, right? So this is what we get from fact 3, and we can generalize it as well, that in case of A plus B whole to the power n, since the general terms are ki a to the power n minus r into b to the power r, that means a to the power n minus r into b to the power r, this term will appear ki times. Here we get fact 3. The coefficient of each term is equal to the total number of times it appears, right? So now, if we want to get the form of these general terms, we want to replace this ki with n, right? Since we know the value of n, so we want to replace the value of ki with n. So we have to determine the value of ki. In other words, we have to determine how many times we get a to the power n minus r into b to the power r. Okay, let's get to this point. As I said here, to determine the generalized coefficient for each of the terms, we'll have to count how many times each of those terms will appear. Okay, how many times it will appear? Let's say if a general term is ki a to the power n minus r into b to the power r, okay, how many b's will be multiplied in this term? How many b's will be there? R number of b's, right? So as we know, in the expansion of a plus b whole to the power n, we can write it like a plus b, a plus b, a plus b, total n times. And we know from fact 1 that each of these factors will contribute one element in each term, right? So out of these total n factors, R of them will provide B. Now there can be a question, which R of these n factors will provide B? Is there only one way? No. See, we can choose the first R options, which will provide B. We can choose the last R option, which will provide B. So b to the power r can appear many times, right? In many ways. So as we can remember from the previous fact that we are supposed to determine how many times we will get a to the power n minus r into b to the power r. Now we will count that. As we know from the definition of combination, there are total n options, right? Here combinations has a great influence on binomial expansion theorem. So among all of these n terms, in how many ways can we choose RB's in CR? How? Why NCR? Out of these n factors, R will provide B, right? So which R of these n options? We can choose these R factors in total NCR ways, right? So there will be total NCR ways to choose B. And how many of the factors will be remaining then? after r of these factors, there will be remaining total n minus r factors. And as we know, each of the factors provides one element. So all of these n minus r options will provide A, and all of the r options will provide B. So the remaining n minus r options will provide A. So NCR, sorry, n minus r, C n minus r. From all of the remaining options, we will take A. And this can be divided into two tasks: taking B's from R factors, taking A's from n minus R factors. So these two tasks must be done. So from the counting principle, product rule of counting principle, we can say that there will be total NCR into n minus R C n minus R ways to choose n minus R number of A's and R number of B's, right? So we get here that there will be total NCR into n minus R C n minus R ways in which we will get a to the power n minus r into b to the power r, right? And as we can remember that n equals to 1, remember that? So this term is n minus r c n minus r, this is equals to 1. So there will be total NCR ways to get a to the power n minus r into b to the power r. So a to the power n minus r into b to the power r will appear this many times. So the coefficient ki, a to the power n minus r b to the power r, coefficient ki refers to the total number of times that this term appears. So ki is equal to NCR. Now what we get here is the representative terms of a plus b whole to the power n will look like NCR a to the power n minus r to b to the power r. Now I have to question that, can you determine the limits for r? I mean, what could possibly be the values of r? Okay, if it is difficult, I can make it easier for you. How? Okay, students, let's say at least how many b's can you pick out of these n factors? Zero b's. That means if you take 0 b's, then how many a's will be there? Yes, all of these n options will provide n, so provide a. So there would be total n number of a's multiplied, that is there will be a to the power n. And since we know there is 0 b's, so what will be the power of b? There will be 0, and the coefficient will be NC0, right? Okay, so we get here that the lowest value for r equals to 0. And what is the highest number of b's we can take from this n factor? Very simple. Since there are n factors and we can take 1 from each of the factors, then there will be highest n number of b's. And in case of n number of b's, how many a's will be there? As we know that if we take n number of b's, then the power of b will be n, and we got that how many a's will be there. We can remember from this general term, if this is n, then this power would be 0, right? And the coefficient will be NCN, right? Okay, so we can say that the limit for r will be 0 less or equals to r less or equals to n, and this is where we get our fact 4. General terms be like ki a to the power n minus r b to the power r, and we determined that ki will be ncr into n minus r cn minus r, that is ncr. That's what we got. And in the expansion of a plus b whole to the power n, each of the terms will look like ncr a to the power n minus r into b to the power r. So at last, time for complete expansion of binomial expansion theorem. How? Say this is the binomial expression, right? And in this case, at first, the first term will be in form ncr a to the power n minus r b to the power r. Okay, so we know that we can choose 0 number of b's at first. If we took 0, that then r equals to 0. So the first term will be looking like nc0 a to the power n minus 0 b to the power 0. It means there will be total nc0 times when we'll get a to the power n into b to the power 0, right? Then the next term, what will be this? At first we took 0 b's, now we can take 1 b's, and if we take 1 b, how many factors will remain? N minus 1. So a's power will be a to the power n minus 1, and nc r, since r equals to 1 here, so this is in my nc1. Next we'll take 2 b's, and then the power of a will be n minus 2, and we'll get 2. At last we will increase the value of r, right? Then 3 a to the power n minus 3 nc3, then 4 a to the power n minus 4 nc4. Similarly, we'll keep on increasing the value of r, and at last in which point the value of r will end? If we take the highest value of r, that is n, we say it here, right? Here n, then a's power will be a to the power n minus n, and nc n here, right? Okay, so what is the expansion of binomial theorem? A plus b whole to the power n equals to nc0 a to the power n plus nc1 a to the power n minus 1 b to the power 1 nc2 a to the power n minus 2 b to the power 2, like this, and at last ncn a to the power 0 to b to the power n. So this is known as binomial expansion theorem, and this is how the idea of combinations is very important in determining or generalizing binomial expansion theorem. Thank you.